Today we're going to talk about teaching and learning computational skills, in particular with MATLAB. This is a topic that's, well, very important to me, but something I've spent a lot of time on. You can see here that a draft poster, that I'll be giving a poster session in a couple of weeks at the European Geoscience Union conference, and there's a lot on this poster, and that gives you a sense of how much there is to share, how many resources are available for teaching computation and quantitative thinking. And so my goal for this webinar is to share many of these resources with you about teaching computation in general with MATLAB, but also more specifically for geoscience, and also for how you can learn MATLAB and computation, because there's a lot that students could benefit from, and also educators who are new to it. So one goal of mine will be to make sure that you can find the resources, and that may sound simple, but a lot of people don't know what's out there, and then even when they know what's out there, they may not know how to find it. So a key aspect of the webinar will be to show you where to look. Often I get asked what things require a MATLAB license and which things might be available at no charge, particularly when you're teaching a classroom of students or working with the public even. You may want to know what's available through the license and not through the license, so I will try to point that out as we go. So the goal of this would be that everybody takes away two things. That would be enough, that if everybody went off and investigated two things they didn't know before, I'd consider that a great success. This is not really about product features. It's really about general resources that would help you maybe introduce product features or other aspects of computation. So this is not the usual webinar where I review a bunch of MATLAB capabilities, just to warn you, okay? So computational thinking has been a big topic. This slide shows some concepts that have been put together by Carnegie Mellon University, and I saw this presented by somebody who's very active in integrating computation into undergraduate physics. She's one of the leaders of a group called Pickup. You can see that there. And she was explaining what computational thinking was. And I think it's important to understand that we don't just mean programming. You can see in the word cloud there, programming is pretty big. But really, it's more about thinking algorithmically, not just the mechanics of programming, but more importantly, perhaps in science, the idea of applying mathematical concepts. So what we're trying to do is get the students to, well, one, understand the science, and then having understood the science or trying to understand the science, figuring out how to express that in programmatically, but in a language that then would enable them to solve problems and get their ideas kind of to produce computational results. And this idea of computation, of course, isn't just in physics, it's in geoscience, it's in many other disciplines. You can see here a study where a number of people have been trying to understand what computation, what skills would be required of undergraduates when they go out into the workforce. And if you read this, you can see that the study, it talks about computation as one of the skills that they need. But there are others, and you can also see that if you look at the results, that in general, academics and employers were pretty much in sync on what was important. You can see, be quantitative, use scientific methods, solve problems, data, right? So clearly we're talking about, if not explicitly talking about tools, we're thinking about the kinds of problems that would require computational tools. So you can see that there's a lot of work that's gone into this and awareness of the kinds of things that undergraduates would need. And this is consistent with what we already know about how math is introduced into curriculums. We all know that you teach and learn Calculus 1 before you teach and learn Calculus 3. We assume that you're going to build on math the way that, and so the question is, why wouldn't you do that the same way throughout a curriculum with computation? And so one of the challenges, but one of the goals is to figure out how to make computation happen logically through a curriculum or through a major or even throughout a school so that students leave with proficiency so they can use it in the job market. And there are a number of indications that, in fact, schools and professors are adopting computation and figuring out ways to introduce it more systematically. One example of this is a new required course at UT Austin also. A senior professor there realized that only 25% of the people in the major, or there are many majors, so in the department, were learning computation, or at least required to learn computation. So the geophysicists had to do computation, but other majors, geology, hydrogeology, didn't necessarily have to. And so they made a required course so that every graduate would have learned computation during the course of their time at the Jackson School of Geoscience. Another example is teaching grants. Educators are getting grants, as you're all aware, in GeoPaths for getting students learning computational thinking, and that this is, this was their abstract, and this is what the money went to. There are books that are not just textbooks, but have code in them, and you can see here MATLAB and design recipes, so that not only can students use the book, they can also access the code and use that to learn and even execute the problems on their computer. And there are online resources as well. This one's called MATLAB Recipes for Earth Science, and in teeny little writing there, you might see course materials. The intent there is to provide tools for instructors so that they can find tools that they can use to teach computation. So you see there's a lot going on, a lot that's out there, and as I said, I'll work through more of it. So now that we know what computational thinking is, or what's meant by that, and what it means or what it might look like to embed it into our curriculums, let's think a little bit about what it means to apply it. And I'm going to share at a very high level some case studies or examples of computation in the workforce, really in applied science. And these focus on resource management and science. There's one that is actually about forest management and detecting problems in forests. This is actually a project that was done by NASA and Lockheed Martin in conjunction with a number of government agencies. And so it's now a viewer, a data viewer, for looking at vegetation and precipitation changes. And anyone could use it. The students could use it. You could use it to go view what's happening with the vegetation over time. MATLAB's behind it. And if you're using it in processing images, you're using MATLAB to do that. Another one that is an example of air quality, and you can see here MATLAB app was used to calculate or and understand the air quality differences. Green is good. You can see good, moderate, and then after that, the app used classification learning, which is a machine learning technique, to understand the air quality. They then map that to the latitude and longitudinal locations to show where the air quality was good and not so good. All right, and this last example is one I'm actually going to walk through. It's an application created by USGS, U.S. Geological Survey. So in this example, USGS is analyzing water flows. It has a job of managing 1,000 waterways in the U.S., and they have a technology called ADCP, or Acoustic Doppler Current Profiler, and they're able to collect 3 million points from a single area and then understand what's happening with the water. How fast is it? How tall is it? How turbulent is it? And this is something that's used by the Army Corps of Engineers and others to manage those waterways. So when they realized that they could do this, they decided to make something called a toolbox. And this toolbox is available to anybody managing the waterways. You can use it on MATLAB, on top of your MATLAB, or you can use it without a MATLAB and then manage the waterways that way. They've written a paper. Oh, sorry, here's where you can download the software from on USGS's site. And they've written a paper about this. Now, it's actually had about 2,000 downloads in a year, so that means people are using it. The reason I mention this is because I think when you're teaching students, it's useful to show them how computation might be applied in real life, in their real work lives. And so this is a great example of people at USGS doing computation and also providing it to other people who need to understand the waterways for them to do computation. And this idea is sometimes called Great Demo. It's a book and a philosophy that came out a few years ago. The idea is that sometimes when you're teaching, it can be a really good idea to start out with a really cool example, what the end result looks like. And so these three stories that I just told to me are examples of the sorts of things you could share with a class before you head off to get them getting down to the details and starting kind of from square one in terms of computation. So you may have different stories that you would want to share in your class, but the idea is to kind of wow them and get them engaged by showing kind of the end result or where they're headed in their career perhaps. But it's nice to tell stories, but I think many of us would agree that the best way to learn computation is actually through doing. And so there's some great examples of professors and other educators using experiential learning and project-based learning to help their students get their feet wet and get engaged with computation. This is an example at Princeton University where the professor takes the students out early on, these are freshmen, and has them drill holes in trees to get tree cores out. And then they use the tree cores, then turn those into images and use the images that they got from looking at the tree rings to analyze the trees and also compare them across students because they're all perhaps looking at different trees. So that's a way to get your students both engaged but also doing their own computation using their own instruments to understand it. And you might wonder, how are they doing some of this work? In fact, some of the projects that students do use MATLAB Mobile, which is MATLAB on via an iPhone or an Android. And you can see that here. And if you go to the MATLAB Mobile page, and the link is up there, you can use MATLAB Mobile even if you don't have a license. That's what this column is. And then there's some more capabilities, but not a lot more available if you do have a license. So that's something that even if not every student in your class had a MATLAB, they could still make use of MATLAB Mobile on their phone. Okay. So that gives you some background on sort of positioning and getting students engaged. I'm now going to move to the resources themselves that are available for you as educators and also for learning MATLAB. So I wanted to share with you a project called, MATLAB Computation, Computation in the Sciences, perhaps, but this is a project done by MATLAB in conjunction with CERC. And what this is first, why should we worry about teaching MATLAB at all in science or math or engineering? Well, it turns out that a lot of faculty are using MATLAB already, and that there are 1,000 schools that have what's called a TAH, Total Academic Headcount or Enterprise License, and universities and colleges. There's more usage than just those, but with 1,000 schools or more than 1,000 having campus-wide access to MATLAB, there are a lot of educators who are choosing to use MATLAB to teach. As I said, though, a lot of them don't know about the resources, and they're busy. They don't have time to go spending a lot of time looking. So CERC and MATLAB decided to collaborate and figure out how to provide more resources for the faculty teaching STEM and computation. And so as a result, we've had multiple 3-day workshops where the faculty get together and work on their curriculums and also compile teaching tips that can then be shared on a website. So basically it's content that's pulled together by the educators for their peers. And you can see here the invitation to last year's webinar. It was the 3rd annual one. And so the problem that we're solving is, for those educators who I speak to, it's often a sort of infinite project. They create a course and they gradually introduce more computational aspects to the course, and then they assess how it's going based on student feedback, and they speak with other professors, and they modify their course. And this is kind of an endless loop. Not in a bad way. It's great that everybody wants to update and improve their course all the time, but it's a lot of work. And so the more we can figure out how to inject pieces into the course or make available pieces that educators could choose from, the more it will make that whole process less time consuming. So these are some of the things that or some of the kinds of things that we looked at in the workshop. We already talked earlier about computational thinking, and you can see here that one of the things Maria is talking about is what mechanism did she use to have the students learn. In this case, simulation. In this case, it's an experiment. Um, Other people talked about teaming. How do you get effective groups in your courses? Princess Imokwede is an expert on that, and people were really interested. Here's a question: how do you make computing fun so that they can learn by playing with MATLAB and experimenting? And then someone else talked about how do you link computation to policy implications and real policy decisions that are being made about our natural resources, and the students got very excited about knowing they understood enough computation to question and evaluate policy. So these are all things that were presented by faculty at the workshop. And as you can see, it turned into a nice website where these tools and best practices are shared. And you can see it here. There's sort of the computational aspects: visualization, computational thinking, data analysis, but also what is it? What do students? How do you organize it and make students effective? Self-efficacy. How do you grade them? That sort of thing. Here's an example, or a list, I should say, of all of the teaching activities, meaning sort of course modules that teachers contributed. There are 82 listed here, and they're broken up by the subject area. So you can just go in and use those. And in fact, I'm going to show an example in a minute. There are also courses available on the site. This is somebody did a very elaborate job putting up a description of week by week of the course to teach computation in 6 weeks to freshmen. And in fact, lists every single, has on downloadable every single piece of the course that they use, the lecture materials, the cheat sheets. But I often have educators ask, can I have the perfect curriculum? Do you have my curriculum? I'm teaching structural geology or hydrology. Do you have something I can use? And really, it turns out once they get into it that they really want to build their own, that they can't just take somebody else's off the shelf. And so the end result is that Circ and MathWorks collaborated to publish components like I was just talking about, the teaching activities, so that educators can choose their own. And so here's one example where somebody contributed an activity that had to do with analyzing global temperature trends, actually having the students compare their results based on data they downloaded to the results that NASA and NOAA came up with. So you can see the teaching activity here described, and then it says activity handout, and this is a excerpt from the activity handout where you can see it's very detailed steps and even code. And then they had the students go. They had to get the file, so you went to the NASA site and pulled down the NetCDF data file. This is all with MATLAB code, and then also computed the result and created the graphic. And so that's the teaching activity. Now, I tried an experiment in preparation for this webinar where I went and got the teaching activity and turned it into a MATLAB script. So what you're seeing here is the MATLAB script. Let me see. It's actually here. I'm now in MATLAB, and this is the same script. And I took the handout and just put comments in so that I wouldn't be trying to run English, right? And I can run this section by section now that it's in MATLAB and actually do the handout, do what the teacher put up on the website. So so you can see on the right there, that the results are actually coming out. And as I do it, because the live script, or it's called live editor, actually displays results. So now I'm computing the average, and then I'm going to get to the big section. I didn't break it up. I probably would if I were teaching. So you can use this as a teaching tool, just like I'm doing now. I would probably break that up into pieces and explain the individual sections. And you can see that little box. It's actually doing doing it now, right? It's actually building the map. And there it is. So, and I just was hovering over this, and it showed me the the longitude, and here it's going to show me the latitude. So I'm doing this very quickly, but I'm suggesting that you use LiveScript as the teaching tool. And you'll notice here I have a copy of the presentation that Janelle Hanrahan, the person who wrote the teaching activity, presented at the CERC workshop. And you can see my results are the same as her results. So it took me only about an hour to take her teaching activity, put it in MATLAB, and figure out how to download the data from the site and get her same result, which is what she has the students do. So that was cool that that I could reproduce her teaching activity. So these teaching activities are available for you to use, and I recommend you might want to peruse them and see if there are any that you might want to make use of for your course. Now, I mentioned Live Editor, and that's the picture of what we were just looking at. Anybody can make a Live Editor. Here's one with physics. It's a document that lets you write essentially narratives with, widgets, meaning like GUI controls and results and graphics. You can see the GUI controls there. So this is available in MATLAB. If you have a copy of MATLAB, you have this. You can just have a Live Editor. But also there's a MATLAB Online, meaning that MATLAB runs in the cloud. So this is something that it looks like this. This is like your MATLAB on your desktop, but it's a little different because it's actually in a web browser. Okay, so one reason you might want to use this is that if you're teaching a class, then all the students would be using the same version as you're using and as each other, and that way you'd know exactly what they have access to. It includes 22 products in the cloud, this cloud version of MATLAB. All right, I'm not going to show this now, but if I clicked on this, it would take me to this kind of view. Okay. Oh, and if you go to the page that describes MATLAB Online, it'll tell you which types of licenses have access. These are all the types. All right. So now that you've been teaching classes and getting activities and all that, and assigning homework to students, you might want to grade their work, right? And so there's a capability that's available at MathWorks called Cody Coursework, which is intended for auto-grading. And you can use some of the existing problem sets, or you could write your own. And what the benefit of that is that it saves you time. You don't have to sit there and hand grade the student's code. It's just automated, so it can test and see whether they got it right. And it can handle any number of students, and you can put as many problem sets up there, optional or otherwise. So actually, to use Cody Coursework, the instructors need a license, but the students don't. You can just assign the students the work to put their code in, and it's just an auto grader. They don't have to have a MATLAB. It's a little odd for them not to have a MATLAB and be doing MATLAB assignments, perhaps. But if there's some way that they have access to MATLAB, they don't need a MATLAB to be tied to their Cody coursework. And they really like it, by the way. They love, if you've ever used WebAssign or any of these other automatic grading systems, students really like it. It gives them direct and automatic feedback or immediate feedback about how they're doing. But talking about assessment tools, programming is not the only thing you want to check for, and I think we know that. And in fact, on the CERC site I was talking about before, some of the activities actually include the grading rubric that the professor used. And this is an example. This one has to do with ocean color and temperature. And the professor says he never gives people 100% credit for coding. In fact, you could get the correct answers, meaning your program ran and did the right thing, and you would only get 50%. You would fail the class if all you did was get correct programming. In fact, he wants to know that their analytical approach made sense. He wants to see their thinking. He wants to see their presentation, which might be a in-class presentation, or it could just be the way they presented it in their homework. So there's a lot of emphasis often in computation put on not just the answer, but all the work around it and how you got to it and how you showed it. To learn more about what's on this site that I'm calling CERC, you can we'll go to the site, but you can also watch a webinar that's available on YouTube. 1,200 people have viewed it so far since it was live cast as a webinar, and it does a nice job of showing some of these activities and pointing you to the site. Another thing, if you're really interested, is there's going to be a 2018 workshop that's similar to the previous ones, and the applications just opened a few weeks ago. I invite anybody to apply who thinks they would benefit from learning. There are many more places to get these resources. Here's an example on the MathWorks site where we have a teaching science section. This one happens to show biology and all this material for biology. There's another one for geoscience. So I invite you to come under our courseware section and see more about that. So there's so many tools. I'm just going to list a few more things that are out there for you to use whenever. This is MATLAB Academy, or sometimes we call it MATLAB OnRamp. There are two free courses I want to draw your attention to. The OnRamp is an interactive 2-hour session where you learn MATLAB by interacting with this sort of application, and it gradually builds up your knowledge of MATLAB. You don't need a license to use this. So there's one that you learn MATLAB from, and there's another where we're teaching deep learning. It's a deep learning OnRamp. One thing that a lot of professors like to do is have their students take the MATLAB OnRamp course themselves before the class starts, before the course that the instructor is teaching, or maybe as the first homework assignment. That way you know that you've got a baseline of all the students having the same MATLAB skill set prior to getting too deep into computation and into the science. And they also get a certificate and a proof that they completed the work, which is really useful to have as sort of a hand-in that the professors can look at. But if you want to do more than that, there are many ways that you can learn MATLAB. Apparently 49,000 ways that you can teach MATLAB in YouTube, but this MOOC is particularly well loved. Excuse me. And there are 250,000 views of that MOOC. And one thing is you don't need to look at the whole thing. Perhaps you just want to teach your students how to plot. So there's a 20-minute segment here on plotting in MATLAB. You could have your students watch just that, right? Then there are more domain-specific ones, such as this one for biologists. But actually, it's really not just for biologists. If you look through the sessions, same thing as the Vanderbilt one. There are individual videos that you can watch about each aspect. And if you, let's say, wanted to learn how to fit data, it's not particular to biology. It would be relevant to anybody who wanted to learn that. There are many more videos, both on the MathWorks site. I think there's about 5,000. On YouTube, I typed in MATLAB Geoscience, and I got 686. But if I type in MATLAB plot, meaning that I want to learn how to plot with MATLAB, there are 178,000. So I encourage you to go searching on whatever it is you want to find, and you'll be able to get probably something on that specific topic that you looked for. So I just want to point out that sometimes even the MOOCs and even the videos, schools sometimes want their students to cover something particular, and so they offer it as a separate sort of almost boot camp. So this previous one was an image processing boot camp with MATLAB that University of Maryland offers. Here's an introduction to MATLAB from MIT offered as part of their Intersession, and another course in Intersession, and another one from Harvard's Compute Fest where they teach deep learning for a couple hours hands-on workshop. So often universities will decide that they need to augment the skills that are coming from the classroom and even make them required before students go into class, much like what I said about the OnRamp. So we've covered everything on the left-hand side, and maybe even some of what's on the right-hand side. There's more. There's tons of books. This is just a sampling of geoscience books. There's tons of MATLAB documentation that's really well written and has a lot of detail and code. There are code examples that you can go searching for, and it often will model for you how to solve a problem. And there's also a site called MATLAB Answers where people ask questions and those questions get answered. I think we're up to close to 200,000 questions and answers now. So if you say wanted to remove image noise from an image, this is an example where someone's asking, how do I crop the green color from the image? And then someone answers and someone else answers, and then the person who asked the question says, thanks, I got what I needed. But you can just go to Google and type that same thing in, and you'll get responses that will often point you to back to MATLAB Answers. But even if, see here, MATLAB Answers and MATLAB Answers, but even if it doesn't, there's some great stuff out there. You just need to Google it, and you'll get an answer to your question without searching too hard. So these are all the things that I talked about. There are some great links here, other things you'd probably be able to find on your own. But like I said, the best way to find all this is to Google it. But if you have the link, you can certainly look there. Again, I appreciate everybody coming, and again, appreciate Kelly and Brandon hosting this. If you have any questions, you know how to reach me. I'm Lisa Kempler at MathWorks, and my information was available as part of the presentation on slide 1.